Hello there and welcome to Lower 6th Further Maths A-Level Pure Core 1 past paper June 2015. Here we're looking at question 5. This is brand new to the syllabus for Pure Core 1. Okay, so determine the values of A and B. So A appears in the third equation and so does B, for which there are infinitely many solutions to the simultaneous equations. Okay, first of all, if there are infinitely many solutions to this system of equations, the first thing we know is that the determinant of this matrix 2, 3, 1, minus 1, 1, 2, A, 1, 4 is going to equal 0. So let's go ahead and work out the value for A that's required to make this matrix have a determinant of 0. So it's going to be 2 bracket and then cross out the row and the column. 4 take away 2 is 2, and then we have to take away 3. Lots of the row and the column cancelled out by the 3 and the determinant left. So minus 4 take away 2a. And the last one, cross out the row and the column for 1. And that's going to be minus 1 minus a. Okay, so let's simplify this. We'll get 4 plus 12 plus 6a minus 1 minus a equals 0. So this will simplify to 5a. That'll make it 16, so equals minus 15. So a is equal to minus 3. Okay, the next part comes to find b by making the simultaneous equations have infinitely many solutions. So what I'm going to do here now is I'm going to start to solve these simultaneous equations, making sure that we get infinitely many solutions at the end. It'd be minus 3 on the end here now. Okay, so the easiest way I can see to eliminate an equation to start with is to eliminate the y variable from equations 2 and 3. So the first thing I'm going to do here is to do 2 take away 3, and I'm going to get here minus x take away minus 3x, that will make 2x. Y take away y is 0. 2z take away 4z is minus 2z, and this will give me 7 minus b. The next way I can see to do this is to do equation 1 take away 3 lots of equation 2. That will eliminate the y variable again. So 2x take away minus 3x, that will give me a 5x. 3y take away 3y, that will give me a 0y, excellent. 3z z take away 6z, that will give me a minus 5z. And 6 take away 21, that will give me a minus 15. Right, so what I can see here is that this equation here is very similar to this equation here. Now, for these to have infinitely many solutions, these numbers at the end here need to effectively match up. If we times this equation by 5, that must match up with the equation here when we times it by 2. So they're effectively the same equation here and here. If these numbers here and here were different, they didn't match up corresponding to the ratios on the coefficients here, then we'd get parallel planes in which we would have no solutions. So we need 5. We need to turn this into a 10x minus 10z. So we'll times this equation by 5. And we need to turn this equation into a 10x minus 10z. So we need to times this equation by 2. So 2 times minus 15. That will make this 35 minus 5b equals minus 30. So to add the 30 on the other side and you get 65. Add the 5b onto the other side, you get 5b. So b will equal 13. So we can see here, we'll test it out. When b is 13, we're going to get 7 minus 13, which is going to give us minus 6. And if you look at the ratios between minus 6 and minus 15, if you times this top one by 5, you get minus 30. Times this bottom one by 2, you're going to get minus 30 as well. So effectively what we have now here and here are two equations that are the same. They overlap, and therefore they must provide infinitely many solutions. What we can do, so that's the answer to pi. Give a geometric interpretation of the three planes formed by the equations. Well, if we have infinitely many solutions, we either have two options. One where it forms a sheaf and it intersects along a line in the 3 dimensions, or all three planes overlap in some way. But looking at the equations here, I can't see that all the equations are equal, or if not a scalar multiple of each other. So it's not this one here, so it must be the one that's left over. The equations form a sheaf. Excellent, 7 marks.